Hi, my name's Eric, and I'm excited to share our team's work on S4ND, modeling images and videos as multidimensional signals using state spaces. A commonality between all state-of-the-art vision architectures is that they model data as discrete pixels, and therefore understand fixed resolutions. But the visual world is made up of multidimensional and naturally continuous signals, where images are just discretizations of these signals. Our key contribution is a model that's both competitive with state-of-the-art architectures and that models the underlying continuous signals, which allows it to adapt to multiple resolutions. A natural approach to building such models, which we build upon, is through continuous convolutions, which use flexible kernel sizes depending on the sample rate and length of the input. Among these are state space models, or SSMs, and in particular, the S4 model, which has achieved state-of-the-art in modeling sequence data derived from continuous signals such as audio, as well as outperforming on sequences in the challenging long-range arena benchmark. A shortfall of S4 is that it's applied only to 1D signals. We propose a new deep learning layer called S4ND that extends work on S4 into multidimensional signals that can be applied to images and videos. For background, SSMs are just a sequence modeling layer. They map input to output through a higher dimensional state. And in S4, by discretizing and unrolling the SSM, we can produce a global convolutional kernel. Our key idea for S4ND is to turn the standard SSM into a multidimensional partial differential equation governed by a different SSM per dimension. With additional structure, we show that it's equivalent to a continuous convolution in n dimensions. This results in an S4ND layer that is fast and easy to implement. Here we show a flowchart on how S4ND is constructed in the 2D setting. First, we initialize the SSM parameters for each S4 kernel. We then create two S4 kernels, one for each dimension, with each kernel spanning the entire input length. We take the outer product to produce a 2D global convolutional kernel, which can now replace regular local 2D conv layers in a deep network. We highlight that S4ND is the first continuous signal model to be competitive with state-of-the-art models on large-scale images and video data. In our experiments, we show that S4ND can be used as a drop-in replacement in modern vision architectures, while boosting or matching performance in 1D, 2D, and 3D classification tasks. For 1D, we start with the vision transformer. For 2D, we use the CNN conv next. When we swap their core operations for S4ND layers and train on ImageNet from scratch, we boost or match performance in all settings. In 3D, we take our pre-trained conv next model and inflate it temporally from 2D to 3D to create a video model baseline. We then swap the 3D conv layers with S4ND and see a 3.5% boost on the HNB video dataset. As a continuous signal model, S4ND also exhibits resolution capabilities that we highlight in two settings. First, in zero-shot resolution, where we train on lower res and test on unseen higher resolutions. In progressive resizing, we show that one can reduce overall training time with S4ND. Since lower resolutions are faster to train, we can gradually upsample throughout training before reaching the final resolution, and still maintain accuracy to within 1%. We also introduce a new band-limiting regularizer that helps both resolution settings and acts as a low-pass filter, removing high frequencies to address aliasing artifacts, which we can control by the SSM as hyperparameters. As a preview in the zero-shot setting, S4ND outperforms a baseline 2D conv model in all settings, in particular by 40 points on CFAR10, when trained on lower 8x8 and tested on higher 32x32 resolutions. To summarize, we presented S4ND, which extends S4 capabilities into n dimensions. We show that S4ND is a strong candidate for a general vision backbone, boosting or matching performance on image and video classification, while exhibiting the ability to train and test at different resolutions. We're excited for what other capabilities S4ND can unlock in both vision and other fields that seek to model continuous signals. Thanks for listening.